So slope fields are a way to visualize the various solutions to a differential equation. And where they're particularly helpful for us in calculus, especially in Calc 1 or Calc 2, is that if we're only able to solve separable differential equations, it makes it hard without use of a slope field to reason about differential equations that are not separable. So we're going to sketch two slope fields in these next examples, and then we'll kind of dig into the understanding of what the slope field means. So for this first one on the left, we are asked to draw a slope field for the differential equation dy over dx equals x plus y. And I just want to point out, like, if our goal was to try to solve this differential equation, so like let's say that I had dy dx equals x plus y. If I multiplied both sides by dx first, I would then have dy equals x plus y times dx, and I cannot get the y to the left-hand side. Like, it's grouped. I can't subtract y from both sides because dy minus y, like one, that doesn't work. It needs to be multiplication. And two, that x plus y is grouped in parentheses. So this is not a separable differential equation. We're not going to be able to find a solution with the strategies that we have right now. All right, so what we can do though is we can draw what we call a slope field. And when we get into multivariable calculus, we'll do this with vectors. We call it a vector or a force field. So when we look at our differential equation, we know that I could think of dy dx as the slope that I get from whatever my solution is. I could think of this as the slope of the solution is found by adding x plus y for every single point that's on this curve. So when I go to find my my slope for any x plus y combination, I'm just going to add x plus y, and that would give me the slope of the curve of that at that particular point. And again, the curve is a solution to the differential equation. This is its derivative. So the strategy that I'm going to use, and it's a lot. This first one's tedious. There's a lot of points. Typically, if we have to do this on an AP exam, we don't have to do it at so many points. I'm going to make a table. And if you're going to do this with me on page 69, I'd encourage you to write really small because we're going to have to fit a bunch of stuff in this table. But I'm going to make a table where I look at the values of x and y that are indicated in this graph. And I'm really only looking at where there are points. So there's still a lot of points though. So my y values are from +2 down the y-axis to -2. So out to the side, I'm just going to do this in order at which I see them. Oops, so +1, not -1. I'm going to write these in the order at which my eyes would view the y-axis. So that's kind of like my y-axis out to the side. And then my x-axis, I need from -3 to 3. So I'm going to say like -3, -2, -1, 0, 1, 2, 3. I'm just going to have to write really small because there's not a lot of space here. So if I think about my slope, so these are just the x and y values that are marked in our graph. But if I think about my slope dy dx is just x plus y. So when I go to find my slopes here, I'm just going to add the x and the y values. So like I like to take it one number across. And our goal here is to look for patterns to make this easy for us. So like -3 plus 2, I know that's like a -1. -2 plus 2 is 0. -1 plus 2 is +1. And I can quickly see that I'm just going to be adding those numbers together. We're going to be counting by ones. All right, so then when I add -3 and 1, so like when x is -3 and y is 1, my slope is -2. So like when x is -2 and y is 1, my slope is -1. So again, I'm just adding these together, but I can quickly discern a pattern here that I don't have to add every single combination together. All right, well, when y equals 0, or sorry, yeah, when y equals 0, and I'm adding that to these various x values, well, anything plus 0 is just itself. So I know I just get -3, -2, -1, 0, 1, 2, 3. All right. As we keep going, when I add -1 to anything, it's just one less. Or by now, I could just look at my table that I'm making out to the side and pick out my pattern. So -4, -3, -2, -1, 0, 1, 2, and then -5, -4, -3, -2, -1, 0, 1. So again, to just like reiterate what this represents, any given slope, I'm just going to arbitrarily choose one. Any number in this collection, in this sort of table that we made out to the side, that is going to be the slope dy dx for some combination x plus y. So I'm adding when x is -2, when y is -1, at the ordered pair, -2, -1, my slope of a solution curve should be -3. So when we go to express this on our slope field, we're going to use little line segments to draw these out. And I personally like to always start with any combination that gives me a 0. So I know like a -2, when x is -2 and y is 2, dy dx is 0. When x is -1 and y is 1, dy dx is 0. So I like to graph all of my zeros first. So I'm going to start at -2, 2 right here. And I'm just going to draw like a little horizontal line segment there. So that has a slope of 0. Then I'm going to go to -1, 1. Then 0, 0. Then 1, -1. Then 2, -2. Now that would be pretty easy to do without making that whole table. The table is optional, but sometimes it helps us when our dy dx is a little bit trickier. Okay, so then I like to go to like a positive one. So I know like for -1, 2, 0, 1, 1, 0, 2, -1, those are going to be all of my positive slopes. So as I look at this table from left to right, I'm going to be able to like graph my slopes in that order on the slope field. And I know I've skipped the first column, but that's okay. So when I get over here and I go to draw my slope at -1, 2, it doesn't have to be perfect. When AP reads these, we don't get out like a protractor and measure it. But what helps me eyeball it is if I want a slope of +1 here, I kind of think about connecting those 2 points. That would have a slope of 1. So I just kind of think about what that would look like, and I draw a little line segment there. So anything else with a slope of 1, it should roughly look like it has about the same slope as the one I drew. They should roughly be parallel. It does not have to be perfect. But now when we get to our ordered pairs that have a slope of 2, so like 0, 2, 1, 1, 2, 0, and 3, -1, now that needs to be steeper. So our slope of 2 needs to visually look steeper than our slope of 1. So again, if I want a slope of 2, I could go like down to back 1 and think like, okay, my slope is roughly the slope of this line segment here. But again, like AP is not going to get out like a protractor and measure this. So we just have to make sure the slope of 2 is steeper than the slope of 1. So then we get to our slope of 3. And that's got to be steeper than the slope of 2. So again, I could kind of envision it. If I go down 1, 2, 3 over 1, that should be about that steep. But it just has to be steeper than our slope of 2. So then our slope of 4 has to be steeper still, and our slope of 5. All right, so that's part of our slope field. I like to do the positive numbers first. I don't know. It doesn't matter what order you go in. That's just how my brain works. And then as we go back to like a -1, I'm going to draw in everything that has a slope of -1. And then everything that has a slope of -2. and then our -3s, the -4s, and the -5s. Okay, so that's a little bit tedious. That's a pretty big slope field. Normally, we don't have to make them by hand, and they're so big. But let's think about what the slope field represents. All right, I just did a copy and paste of the slope field that we made. And remember, our original differential equation was dy dx equals x plus y. So if we want to understand what this is helping us visualize, let's say that I picked a point at 1, 1. I'm going to draw 1, 1 on my graph. 1, 1, that could be a point that is on the curve that is the solution to this differential equation. So if I were to trace this pattern, I'm going to kind of get caught up in the direction of the slope, and it'll get steeper and steeper. As I go to the left, it's getting like less steep. It's going to hit like 0 here, right? And then it starts going back up. But I could see that there's like this line, this diagonal line that goes through the middle of my slope field. And so if it gets caught up, or if it gets really close to that line, it's not going to, like the curve I just drew isn't gonna go underneath the line. So it's kind of like, if I think of the slope field almost as like a current, it's like I'm getting kind of caught up in my slope field here. Now, it's hard to say that this is perfectly accurate, but if I look at this, this is representing visually a solution to this differential equation. Like a solution is going to be some curve in the form of y equals. And again, like the examples we did on the previous page, we were solving differential equations. We can do that when they're separable, but dy dx equals x plus y is not separable. So this curve represents a solution we would get if we plugged in the initial condition 1, 1, because the point that I chose to be on the curve is 1, 1. But it's not the only solution. We know antiderivatives, that there's infinitely many antiderivatives for any one function because of a constant of integration. Similarly, there's infinitely many solutions to a differential equation for sort of the same reason. So if I had picked a different initial condition, like let's say that I draw the solution curve that goes through the ordered pair -1, -2, I'm going to get caught up in the curve there. So I'm going to follow the slopes, and it's going to look something like this. And so, and I think going down, it gets steeper and steeper and steeper. So notice that that looks a lot different than the first solution curve that we drew. Because we used a different initial condition, we're going to get a different solution curve in our slope field. So our slope field is a visual representation of the possible solution curves for this differential equation. So going back to the example as it was presented in our text, there was one other thing besides drawing a solution curve. There's something else we might be asked. We might be asked to reason about our differential equation, given the information we have. So we're asked to describe the region and the xy plane for which the solution curves are concave up. And we have to be careful with the word describe. That may or may not really necessitate us saying anything in words. That may end up like a few mathematical statements. So I know that if a curve or just a function in general is concave up, I know that means my second derivative is positive. So we're given dy dx. We want to take the second derivative. So the first derivative of dy dx, I'm going to get, well, the derivative of x with respect to x is just 1. And the derivative of y with respect to x is just y prime or dy dx. So what I end up getting when I actually substitute x plus y for y prime or for dy dx, I get 1 plus x plus y. So our second derivative is 1 plus x plus y. So if I know that my second derivative must be positive, that means 1 plus x plus y must be greater than 0. So I would probably just isolate y. So that means y must be greater than negative x minus 1. So going back to our actual curve here, if we notice, or to our slope field rather, if we notice that this horizontal line that I drew with a highlighter is negative x minus 1, like if I were to actually draw that horizontal line through there, if I look at everything above that, all the solution curves that I would get above that would be concave up, and all the solution curves from below that would be concave down. And again, sometimes it's helpful to like visualize that when we actually draw in the solution curves. All right, let's look at one more example. And again, it really helps me to make this little table. This one's a little less tedious. So in our second example, our differential equation is 2 minus y over x squared. And so notice that we don't have a point. We have 16 points indicated below, but we don't have a point like everywhere on our graph. So when, again, I'm just going to, oh no. Okay, I'm going to just write out my y values. So if I look at my y values, I've got a 3, 2, 1, 0, and negative 1. And then my x values, I know I'm kind of writing off screen here. I'm going to have negative 2, negative 1, 0, 1, and 2. So the first thing I want you to notice is on our y-axis, where x equals 0, they're never having us find the slope there. And usually, almost always, that's going to happen for one reason, and our slope is probably undefined there. So if I look at plugging x equals 0 into my differential equation, I'll be dividing by 0. That would have a vertical slope. So I am just going to not find any slopes when x is 0. I mean, it would be infinitely sloping. I also notice when I look at my differential equation that my denominator is always x squared. So that's going to help me have a little symmetry, I think, when we go to find our slopes here. So again, I might either start with what's easiest or start with where I see a pattern. But if my slope is 2 minus y, so when y is when y is positive 3, my numerator is just always going to be negative 1, because 2 minus y, 2 minus 3 is negative 1. So for my first slope, I'm going to get negative 1 divided by x squared. Negative 2 squared is 4. And then for my next one, because again, I only need y for my numerator, so I get negative 1 divided by x squared. Negative 1 squared is 1. So that's just the slope of negative 1. Over here, my numerator is still negative 1. My denominator is also 1. And here's that symmetry that I'm going to get another negative 1/4, because my numerator is negative from the y equals 3, and my denominator is always positive. All right, so we'll kind of notice this pattern as we go down making our slope field. Now, when y equals 2, anytime that y is equal to 2, my slope is 0. So, with the exception of 0 over 0, I'm going to put zeros all the way across. All right, anytime my slope is positive 1, 2 minus 1 is 1. So these slopes are going to be the same as when my slope was, my y value was 3, except they're just positive numbers. So again, we can kind of look for these patterns in our reasoning to help us do this quickly. All right, when my slope is 0, my numerator is just always going to be 2. So I've got 2/4. So 2/4 is 1/2. 2 over 1, 2 over 1, 2/4 again. And then finally, when y is negative 1, my numerator is 2 minus negative 1, which is 3. So we end up getting 3/4, 3 over 1, 3 over 1, 3 over 4. So again, I'm just quickly plugging in x and y to that equation for dy dx. So again, as we're making our slope field, you could do it however you want. My pro tip is to start with where we see zeros. So we said anytime y is 2, so I'm going to go up to where y is 2. And I'm just going to put a slope of 0 here. I'm not going to put a slope of 0 on the y-axis because we would be dividing by 0 there. All right, and then up above where I got the slope -1/4, it turns out that we don't actually have a point there or there in my slope field. I just got a little carried away. So if I go up above, my slope should be -1 for when y equals 3 and x is 1 or -1. So again, as I'm estimating my slope of -1, it doesn't have to be perfect, but roughly it should look like that. All right, beneath that, I'm looking at where I have my positive ones. And then I know going to the left, I have a slope of approximately 1/4 on the left and the right of the points I just made. So I could think like up 1/4, that's going to be pretty flat. It does not have to be perfect. It just has to be a lot less steep than the 1. All right, then if we go down beneath that, beneath our 1s, this is where our slopes were 2 and 2. So 2 and 2. I'm just going to do the vertical ones first. So then 3 and 3, 3 and 3. And again, it doesn't have to be perfect, but my slope of 3/4 for each of these. Oh wait, no, I'm sorry, not my slope of 3/4. We don't have to do 3/4. My slopes of 1/2 when y equals 0, those just have to be roughly a half. It doesn't have to be perfect. It's like maybe here and here. Okay. All right, so this is our slope field, again, for dy dx equals 2 minus y over x squared. The next thing that we are asked to do is to describe the region in the xy plane for which the solution curves have a positive slope. Now, we could probably just reason about that from our table, from our slope field, but I know if my solution curves have a positive slope, that means dy dx is positive. So if I look at dy dx and I kind of just analyze it, the denominator x squared is always going to be positive except for when I plug in 0 for x. So my denominator is always positive. So that means that I would also need my numerator to be positive. So that means 2 minus y has to be greater than 0. So if I add y to both sides, 2 is greater than y, meaning that y has to be less than 2. So again, I can confirm that when y is less than 2 in my slope field, that I'm going to have a positive slope. However, my answer is incomplete because in addition to y being less than 2, x cannot be equal to 0. So these are two things that both must be true for me to have a positive slope. Because if y is 2 but x is 0, technically dy dx is not going to be defined there.